All right, so from one other thing we could do, and by the way, there's no place to do this on your worksheet, so just kind of bear with me a little bit. Um, we have I equals I max, and we did that for the circuit where we threw the switch and the current was started high and started to decrease itself down because it was slowly but surely causing back pressure on the capacitor, right? So this was our situation. Now we could very cutely get around having to do we could find charge in that situation as well. How do we find charge in that situation? Well, we did it for when we moved the battery. Okay. In that case, also the charge decreased, and it interesting enough looked a very similar sort of way. But I want to figure out, in this case, the charge is going to increase on the capacitor. It's going to increase because we have current going into that capacitor, right? And so what I'm going to do here is I'm going to rewrite this as dq dt. Now we're going to note the following: if I say dq dt, I'm actually talking about current, right? Change in charge with respect to time, that is current, right? So no change there. I max, we said, was just the voltage at the very beginning and all the way throughout over the resistance. The voltage of the battery divided by the resistance of the resistor tells me my current at the maximum possible time. And this is e to the negative t over RC. Now, that's beautiful. Differential equation, dq, integral over here. I'm going to pull the VR out because I'm lazy. Integral e to the negative t over RC dt. Now, unfortunately, that is not just a t. It is a big mess, so I got to set u equal to negative t over RC. Du, therefore, equals negative 1 over RC dt. So when I set this thing up, I'm going to need to go V over R. I need a negative 1 over RC here. So I'm going to have to put a negative RC on top over 1, right, out in front. E to the negative T over RC. Left side just becomes Q, right? Q is equal to, these R's cancel out, and I get negative VC. And I'm going to integrate e to the u du. And then I'm going to get negative VC equals e to the u plus some constant. Let's not worry about constant. That'd be some sort of charge we initially started with. We did not start with charge on the capacitor, so I don't have to worry about that. That would be 0, right? Okay. So then I'm going to go a little bit farther. Oh, and when I integrate this, I'm 0 to some time t in the future. So I'm going to do 0 to some time t in the future. Now this becomes problematic. Why? Well, because when I put everything back in, oh, hold on, I shouldn't have done 0 to t. Because remember, I got a variable change here. Your calculus teacher would be freaking out right now. It's like, what are you doing? You can't do it like that. So I wanted 0 to, let me erase it here too, because that's not right either. Okay. Then my pen, my marker back. And so we were doing 0 to some time t here, right? From time equals 0, throw the switch to time equals t. Now the problem, of course, is now when I go ahead and put my variables back in, e to the negative 1 over RC from 0 to t. There's still a t here. What happens is this. When I plug in a t, I get this thing that I expect. Q equals VC, negative VC I should have, e to the negative 1 over RCT, not really shocking, minus, when I plug in a 0, this whole back end becomes 1, and it gives me negative VC. And so I get Q equals, well, that's positive, so I can rewrite this as VC minus VC e to the negative 1 over RCT. Going further, I can rewrite this as Q equals VC 1 minus e to the negative 1 over RCT in my parentheses. VC, VC happens to be my, well, if I go VC equals Q from our previous thing, we notice VC equals Q. So this is Q, but it's my voltage of the battery. So this is going to be my maximum voltage, which means this is going to be my maximum current. Sorry, maximum charge. 1 minus e to the negative 1 over RCT. And so I end up with, an expression that basically says my Q equals my Q max, parentheses 1 minus e to the negative 1 over RCT. Now notice the following. The back end of this expression, this part of the expression here, is my decreasing amount. It's literally the same thing as this thing over here when we were talking about decreasing. But if I take the amount I want to get to minus how fast is the current is decreasing, I can actually get how much charge is piling up on my capacitor. I know I didn't say that right, but suffice it to say that this is true after a bunch of boogie-boo magic. Now, why is this important and what kind of patterns am I seeing? Well, it's interesting. When I have things decreasing, I get this expression. When I have something increasing, I get this expression. And it turns out, because Kirchhoff's law always looks the same, because I'm always going to end up with a 1 over. Where's my 1 over? Because I'm always end up with my 1 over when I'm moving things over, I'm always going to end up with an ln, which means I'm always going to end up with e. I'm always going to end up with an extra RC. So these expressions start to show everywhere. The exact same thing, right? So what happens is this. File new. It doesn't matter whether you're looking for voltage on the capacitor, which is changing, current in the system, if it's changing, or charge on a capacitor when it's changing. All three of these act exactly the same way as long as you know the following. Is it decreasing or increasing? If it is decreasing, if the thing is decreasing, I would say x equals x max e to the negative t over RC. And if it's increasing, it's decreasing. If it's increasing, well then I'm going to go x equals x max x equals x max 1 minus e to the negative t over RC. Now, physicists know us for a long time, and we're lazy. We're so lazy, we don't even want to write down the RC because that would be so hard to do. Yes, I don't completely understand that myself. And so really what we're going to do is we're going to end up writing it like this. We're going to x equals x max e to the negative t over tau. And x equals x max 1 minus e to the negative t over tau. Okay? And that tau is clearly going to be RC. We call this tau a time constant. And it's important enough, AP Central has actually asked a question, hey, what's the time constant for this thing? I didn't used to teach time constant, just skip it. It's 1 over RC, you guys know that. Just do it. No, you can't do that anymore because they'll ask that question. So for an RC circuit, the time constant is RC. Now, I just said something intriguing. Are there other time constants? The answer is yes. We're going to learn about inductors. We're going to do an LR circuit. L stands for inductor. Yeah, I know it doesn't make sense to me. We've got current being I, so you're stuck. But LR is an inductor circuit, and that inductor circuit is going to have a different time constant. But it's going to work exactly the same way. If it's decreased, it's going to use the equation on the left. If it's increased, it's going to use the equation on the right. And the tau is just going to be a different tau because you're talking about inductor. Well, obviously, it changes the time constant. Oh, crazy talk. Oh, crazy talk. So you don't have to be able to do the calculus. You can, and sometimes maybe Santa, kind of throws a wrench in the works and says, hey, figure out what the, from original principles derived using Kirchhoff's law, the equation for the time of a current going through the system. In which case, what they want you to do is start with Kirchhoff's law, and then end up at, if it's a decreasing system, what you end up with this. Okay? All right. So how does this work? Okay, I'd like you to try the very next problem on that sheet. It's labeled example, and we'd like you to try the example problem and see how that goes. If you can get the example problem done and do it right, we are probably in a really happy place. If not, we're probably not nearly a happy place. All right, I'm going to pause this one up. I'm actually going to stop this video, and I'm going to get you another one for the next part.